Thank you so much for the introduction, and thank you so much for joining me for my talk today. Today I'm going to be focusing on reverse engineering for satellite communications. A little bit about my background. I have been in software for about a decade now, and within the past year or so, I got into cybersecurity, and currently I'm doing research specifically for aerospace systems, producing content, also doing my independent research on satellites, as well as aviation and UAV technology as well. So when you think of reverse engineering, a few topics might come up to your head. Things like IDA Pro, like common disassemblers or static analyzers. However, satellites are a little bit of a different ballgame. Whenever you're thinking about reverse engineering from a satellite perspective, it has a lot to do with radio frequency analysis alongside packet dissection. And today I'll be doing a conceptual overview of how you can reverse engineer satellite communication signals by applying your RF and your packet reverse engineering background to a different medium. So whenever you're dealing with satellite technology and communications in regards to satellites, typical data that is being transmitted on satellite communication links include telemetry, so this could be data logs, operational status updates, remote sensing information. A lot of weather satellites send down scientific research and observational data alongside imagery, and you can also intercept text and call transmissions that are used by telecommunication satellites. So a typical procedure of a reverse engineering application in regards to a satellite looks kind of like this. Firstly, you need to conduct relevant reconnaissance on the target satellite using open source intelligence and other techniques. And then you move on to analyzing the communication protocols. Different satellites have different communication protocols based off of their application, and there's different protocols such as CCSDS and other transmission types that might be proprietary that you have to understand in order to dissect its communications. Then we'll go over software analysis, where you can reverse engineer and fuzz for firmware that's running internally within the satellite onboard computer and data bus systems. And lastly, we'll cover how you can identify vulnerabilities. So phase one consists of research, where you're trying to gather as much information about the satellite communications infrastructure. And the four main things you're looking for when you're conducting a reverse engineering procedure on a satellite include the following. Firstly are the relevant components within the satellite communication subsystem. So this will include things like the antennas it's using, what frequency bands they're located in, what frequencies they're using, alongside any other auxiliary communications components that might be located on the satellite. Radio frequency information, so this includes the frequency bands it operates on, the uplink communication frequency, and the downlink communication frequency. Protocols and bus systems. So all satellites have an internal bus system, and they might be using something standard, such as like ARINC, or their own proprietary code format, alongside the protocol that's used to send packets to the satellite and back down via the downlink. And lastly, satellite's a little bit different compared to traditional reverse engineering scenarios, because satellites are consistently within orbit, meaning that you have a very specific narrow time limit when you could get access to communicating with the satellite and receiving information from the satellite. So you need to have a good understanding of orbital mechanics in order to target and pinpoint when the satellite is exactly overhead of you, so you can use the relevant communications technology in order to get access to it. So when it comes to the reconnaissance phase, open source intelligence will be your best friend. There's a lot of publicly accessible information about satellites that are made accessible via sites such as like SatNow or N2IO that give relevant information about a target satellite. And typically you're trying to figure out the mission and the objective of the satellite, which will help lead you to the packet protocols it may be utilizing. Data sheets are also incredibly helpful because they will outline the radio frequency characteristics of the onboard components, alongside utilizing publicly accessible websites to extract real-time satellite orbital details. As for the key communication components, most satellites have a transceiver on board, meaning that they have transmission and reception capabilities. They'll also have a modulator and a demodulator. A modulator converts digital data, so you have a binary that's being processed into a radio frequency wave, so it can be transmitted across space to a ground station on the ground. The demodulator does the opposite sequence, where when you have a radio frequency wave propagation, you can convert it back down to digital binary, and then the amplifier, which boosts the strength of the signal. Other communications components include the up converter. The up converter increases the signal frequency. The down converter does the opposite. It decreases the signal frequency. The decoder converts coded data into the original data, and then the encoder puts the data into a binary format. So just going over basic terminology for reverse engineering radio frequency waves. So all radio frequency emissions look like this. It follows a standard wave structure, and all waves have something called an amplitude, which determines how much energy the wave has and how big the wave is, and a cycle. The cycle dictates how fast the wave goes and the frequency of the radio frequency propagation. So this is a typical electromagnetic wave with 1 hertz, meaning it cycles at 1 wavelength per second. And radio transmissions by satellites operate across a band, because whenever you have multiple satellite constellations that are cooperating or within orbit, they dedicate different partitions of the electromagnetic spectrum based off of their relevant applications. So this is what the electromagnetic spectrum looks like, and usually satellite infrastructure works from the visible band up to the left of the chart, to the radio band. There's not a lot of communication satellites that use the optical band yet, so most satellites will operate within the radio to microwave range. This is a typical layout of a satellite communications electromagnetic spectrum, and you can see that they're partitioned into different segments. The band segments include the L, the S, the C, the X, the KU, the K, and the KA band. And the way they're allocated to different satellites depends on the application of the satellites. So you see things such as radio astronomy satellites or scientific research satellites. A lot of them are within the KA band because they need that longer wavelength in order to research relevant astronomical phenomena, while more telecommunication bands are located near like the X or the KU segments of the spectrum. So this is a typical simplified diagram of the Satcom architecture. Whenever you have any form of satellite communication, you'll have a ground station and you have the satellite, which is the target. And as depicted, the upward pointing arrow is called the uplink, and then the download, the arrow that's pointing downward is called the downlink. Data that's sent via the uplink are things such as telecommands, which tell the satellite what to do. So typically you have things that change the orientation of the satellite, the attitude of the satellite. You can also send sequences of commands, over-the-air updates, payload information, so forth. The downlink is typically reserved for telemetry, any data the satellite is connecting and is collecting and wants to send down real time for collection of for relevant personnel. So this could include weather imagery by weather satellites alongside other remote sensing information. When you look at the Satcom architecture from a macroscopic point of view, you have 4 core segments, but the main 3 include the ground segment, which communicates to the satellite bidirectionally, and then you have the user segment, which is often reserved for commercial use cases, such as telecommunications, where you just need the satellite to beam down information to relevant users. So there's a wide range of publicly accessible websites you can reference in order to get information about a target satellite. The main ones I like to use for my own research include N2IO in order to get positioning and orientation information. SatNow includes a wide array of satellite component catalogs, which include things such as like antennas, and it will list out the frequencies and the frequency ranges alongside the polarization. So it also includes like a PDF of the data sheet, which you can download, which is really helpful for nitpicky pen testing requirements. And then SatBeams, kind of like a combination of the two. And core characteristics that I look for whenever I'm trying to audit for a target satellite include the organization it's affiliated with, any launch slot providers it might be affiliated with, if it's a AMSAT, alongside the mission criteria. Oftentimes the mission will determine what kind of payload information it might be sending out, or the structure of the telecommands you're trying to send via the uplink to the satellite, alongside subsystem information. So satellites have different subsystems, which are groupings of components that determine what to do. So, for example, it might have a subsystem to change its attitude, a subsystem to control the power within the satellite, another subsystem reserved for communications, and you can use websites such as SatNow in order to dissect the specific components within the subsystems in order to figure out how to effectively communicate with them. As for location-based information, N2IO and SatBeam are pretty good references, and you can use it to pinpoint the location of the satellite overhead alongside the infrastructure it is utilizing. And sites like N2IO will give you live orbital information where you can get and extract orbital elements alongside the ground track of the satellite. So the communication subsystem is the main point of focus whenever you're trying to conduct a reverse engineering scenario. And the communication subsystem often consists of a TTNC, telemetry tracking and control, which monitors the health of the satellite alongside collecting relevant telemetry. You have the onboard computer, which is kind of like the brains of the satellite. This is eventually the final target you're trying to exploit, which processes commands and operates the satellite by communicating internally with the various subsystems, and the command and data handling system, which is responsible for managing all the communications that take place. So this is an example of a data sheet that you can download using one of the publicly accessible website references. And whenever you're trying to conduct a signals intelligence or reverse engineering scenario, I typically look for these characteristics. So the frequency and band will be your most important. You need to understand which band it's operating on alongside the frequency range for both the uplink and the downlink. The radio frequency power, modulation schemes are also important. A lot of satellite transceivers use BPSK, but you also see variations such as QPSK, OQPSK, and SQPN. The data rate, the impedance, the noise, and the operating ranges for various subsystems. So you can have operating ranges for temperature, which is determined by the electronics on board of the satellite. Since onboard satellite electronics are pretty resilient, you will have an operating range that's pretty skewed one side and the other. But if you were to exploit a satellite or conduct a scenario where you send a nefarious payload to the satellite that causes it to, for example, rotate its solar panels so it gets more sunlight exposure, then you can fry the electronics on the satellite, and that'll be a pretty readily accessible communications-based exploit. Other operating ranges include power alongside voltage. So once you're done conducting reconnaissance on your target satellite, then you move on to the next phase, which includes tracking. Like I mentioned before, a lot of satellite communications reverse engineering is temporal, meaning that you only get access to a satellite within a specific timing window due to how fast it moves within orbit. In order to find out where a satellite is oriented above you, you need to understand something called orbital mechanics. And orbits are determined by 6 core characteristics known as the Keplerian elements. They consist of the semi-major axis, which is the altitude of the satellite above you, the eccentricity, which is like the stretchiness of the orbit. An eccentricity of 0 would dictate like a perfect circular orbit, like shown here. While an eccentricity closer to 1 would be a more skewed, spread apart orbit. Inclination, which is the tilt of the orbit, longitude of the ascending node, the argument of periapsis, and mean anomaly, which all determine the orientation and the positioning of the satellite. There's a standardized way of readily accessing orbital element and positioning information about satellites, and that's called a TLE, which stands for two-line element sets. And it consists of 2 to 3 lines. The first line is reserved for the name of the satellite. So this is a weather satellite called GOES. And the 2 lines below it include positioning information alongside other characteristics. So both lines will include an international designator, which is a standardized way of identifying the satellite. And the first line includes timing and velocity and relevant motional information about the satellite. So it will include the first derivative of mean motion, the drag term, and a checksum appended to the end of it. And then the second line includes all the 6 orbital element data numerically and has a epoch and checksum digit format added to the end of it. As for understanding the trajectory of a satellite, the ground track is a best reference to understand where it is going over time and what countries or what locations it will be passing later on within its orbit. And one last core characteristic to orient an antenna. So let's say you were doing a scenario where you were using your own antenna in order to intercept communications, is the azimuth and elevation angles. The azimuth is a horizontal angle determining where the observer is relevant to the satellite. So it would be like if I were to have an antenna in my hand, the azimuth would be in this direction. And then the elevation will be the vertical component of it. So it will be the up and down orientation angle. And there's a lot of accessible mobile applications that give you both the azimuth and the elevation depicted on the right is Satellite Finder, which shows you an array of multiple satellites, such as EchoStar, and I think they have GOES as well, that allows you to orient both the azimuth and the elevation in order to properly position your angle for best communication interception. Location is also important, making sure that whichever satellite you're trying to track down is within line of sight. You also want to avoid obstructions that could interfere with the radio frequency transmissions that are occurring from the satellite back down to the observer. So you want to avoid anything that could interfere with that, which includes big buildings, mountains, or trees. You also want to be at a higher elevation, which gives you a higher reference viewpoint and minimizes radio interference. As for weather, there's specific atmospheric and meteorological conditions that could attenuate, meaning to weaken a satellite signal. One of the most catastrophic events that could happen is an effect called rain fade, where you have a cloud with lots of condensed water droplets embedded inside of it that could cause scattering internally within the cloud itself, which causes errors within the data that's being transmitted in the data, or no reception at all. Other atmospheric conditions that are not, that could attenuate satellite signals include any other precipitation, dust, aerosols in the environment, as well as storms. As for pass timing itself, when you are in a scenario where you're about to intercept a satellite signal using your own personal antenna, you're going to have an effect called Doppler shift. This is because as the satellite moves closer to you, the frequency of the wave will be higher, and as it moves away from you, the frequency of the wave will go lower. So that could manipulate some of the data you're trying to intercept from a satellite. And whenever you're trying to run a pass timing objective, getting a timing window, this is a snapshot I took from N2IO's website, which gives you the start and ending azimuth and elevation angles, and making sure that you follow the satellite. It's usually in an arc shape, by also taking into account the Doppler shift that may occur in the environment. And usually if you have a handheld radio that's reserved for satellite communications, you could manually set the Doppler shift within the radio itself in order to account for it. I mentioned N2IO before, but the two other sites I like to reference are Cellestrack and if you want something locally on your machine that you can use at all times and has more features, such as saving satellite constellations, or you can manipulate your own satellite environments by adding your favorite satellites, or having your own up-to-date TLE datasets, I would recommend using gpredict. This brings us into phase 3, which is using communications equipment in order to tune into satellite communications. So when it comes to antennas, you have a wide range of options you can pick from. Personally, I like using Yagi antennas, but you can also use other configurations, such you can go a more omnidirectional route and use a turnstile antenna, or you can use something like a patch antenna if you're trying to target a specific satellite constellation like Iridium. Two main characteristics when you're trying to find an antenna is the mission objective of the satellite. Satellite uplinks and downlinks are most of the time they're different, so you might need different antennas. Moreover, they depend on the application of the satellite, so just because one antenna works for one satellite, it probably won't work. You can't interchange it for another satellite target. You you should also take into account directionality. Antennas with high gain are very directional. So the Yagi antenna depicted above is a very directional satellite, but you are compromising for the beam width, meaning that you need to be very precise with how you orient the antenna, or else you won't get high quality data. If you go the omnidirectional route, you will have a high beam width, meaning that you need to do less busy work trying to get signal reception from the satellite. However, it does come at the cost of interference, where you might get errors that pop up within the data transmissions, or general issues that might come up with the reverse engineering process because of atmospheric attenuations. This is a simple block diagram. A block diagram is used to understand the communications processes that occur when you're trying to conduct a reverse engineering scenario. So in a simplified diagram, you have the satellite, and then you have the ground station. And this is a case scenario where the satellite is beaming down information to the ground station. And if we break it down even further, this is what it would look like. The satellite, the first stage would be an encoder, so you have binary internally within the satellite. So in this case, this would be like an image that's stored as binary. Then it goes through a modulator where it's converted into a radio frequency transmission. It goes through an up converter where it is amplified. And then it is propagated across space using a transmitter antenna, also known as a TX antenna. Once it goes through the atmosphere and through space, it is received by a ground station, which has a receiver antenna. And then it goes through a sequence of events where it is demodulated back down to binary, and then decoded. And this is a reception case scenario, which I just described. And whenever you're receiving any kind of satellite signals transmission, I would recommend getting a software-defined radio. And the SDR you want to get depends on the application itself. You could get something that's very cheap and reliable, such as the RTL SDR. It's half duplex and operates on the 25 megahertz to 1.7 gigahertz frequency range. However, there are more robust options that are accessible, such as Lime SDR and HackRF. The good thing about Lime SDR is that it has a pretty good transmission range capability support, and it is full duplex, meaning that it can both receive and transmit. However, with the RTL SDR and the HackRF, they're both half duplex. I think the HackRF is actually full duplex. I might be wrong with that. But when you're looking for a software-defined radio, you're typically looking for its transmission and reception capabilities alongside its frequency range support. And once you are able to receive and process those signals, this is where it comes to the fun reverse engineering part. We're trying to extract data from the radio frequency propagations in order to interpret it and get your expected outcome. And when you're trying to reverse engineer these signals, you first need to understand the modulation scheme of the satellite. So whenever a satellite is propagating information across space using a radio frequency wave, it will alter the characteristics of the wave in order to encode binary. So there's three primary ways of doing this. Amplitude shift keying. This is where you vary the amplitude of the wave in order to encode information. So usually you have like a low amplitude that indicates 0 and a high amplitude that indicates 1, and you chain them together in order to get your binary sequence. You have frequency shift keying, where you associate a low frequency with 0, and then a higher, more faster phased frequency with 1, and then phase shift keying, where you alter the phase of the wave in order to encode data. This brings us into constellation diagrams. When you're interpreting a satellite signal using some kind of SDR provider or frequency visualizer software, you'll come across these circle shapes that have dots on them. And this will indicate to you how the data is being transmitted and the modulation scheme of the satellite. So when you're running a constellation diagram and you see the just 2 dots, that indicates that the satellite transceiver is using BPSK. And then so forth, you add more states as you add more states of binaries. So when you have 4 states, 0, 1, 1, 1, 0, 0, 1, 0, in a QPSK format, it looks like that. And then in an 8 PSK format, you have like 8 dots around a circle. And this is the most reliable way of pinpointing what kind of modulation scheme a transceiver on a satellite is using. As for decoding, satellites vary, meaning that they might be using their own encryption scheme. However, with a lot of lower tier satellites, often by satellites or CubeSats, they are using a traditional encryption scheme. AES is pretty common, so you might see some kind of symmetric key algorithms used. SHA is also a frequent hash function that's used within satellite communications, alongside secure key exchanges like the X509 RSA key and the Diffie-Hellman. Once you decode the data that's being sent by a satellite transmission, then it gets to parsing. And when we talk about protocol suites, a lot of satellites will adhere to a specific protocol. Vulnerable satellites use something like TCP/IP, and usually that's for satellites that work for terrestrial network systems, because it enables a lot of interoperability and has delays and packet loss. However, there's a standardized space packet format called CCSDS, which is specifically tailored for spacecraft and allows for faster and more cohesive error checking. And that's outlined in the CCSDS Blue Book series, which completely covers all the characteristics and packet structure frames within the space packet protocol. So looking into CCSDS a little bit further and referencing it to the standard OSI model, you can see that on the physical layer, it uses radio frequency waves. On the data link, it uses channel coding and synchronization. And then it also uses custom data formats layered on top of virtual channels and protocols. Here's a screenshot of the CCSDS space packet protocol I took from the Blue Book series. And you can see that the space packet, it's relatively simple. It has a packet primary header, and appended to the back of it is the data field. The data field is partitioned into 2 segments. It has the secondary header, which includes more metadata about the packet itself, alongside the user data field. And if we look into the headers a little bit deeper, you see that each packet has its own version number alongside identification. So it'll have an API ID, sequence flags, and length information alongside a time code and any ancillary data field that isn't included in the user data field. And if a space packet protocol that's being used for a satellite system does include some kind of redundancy or error checking. It will use parity checking, which includes an extra bit at the end of a packet indicating error. So for example, 1 would be even and 0 would be equal, would be an odd case scenario indicating no error. And typical error detection systems that are used for satellite communication specifically include CRC with a appended checksum at the end of it. And for checking itself, FEC is a pretty common error checking standard alongside BCH and LDPC codes. When you're trying to conduct a reverse engineering scenario, key utilities you can use that are free for satellite communications reverse engineering include GNU Radio. I really like GNU Radio because it supports a wide range of formats and standards such as CCSDS. For smaller mid-range amateur radio satellites, it has AX105 support alongside other transmission protocols. SatDump's really nice because it'll give you a visual indication of a lot of the communications that's going on internally with the satellite. It will give you a visual modulation depiction alongside any constellation diagrams you might be getting. And then Wireshark. Once you have a consolidated PCAP of packets, after running it through, once you get through the demodulation phase and you get a sequence of packets together, then you can go through packet dissection and reverse engineering each of the independent packets and associating it with like either the CCSDS protocol or its own proprietary reverse engineered protocol in order to get your encoded data output. Some plugins I would recommend you get for GNU Radio include GR satellites. This will provide telemetry decoding support for most amateur radio satellites. CCSDS supports Reed-Solomon coded CCSDS frames. I think it's about to be retired soon, but for the time being, it still works. And then if you are trying to reverse engineer more like telecommunications-based satellites, I would recommend GR DVB GSE, which is a standard decoder for DVB standard 2 satellites. As for Wireshark, it's a little bit more tricky because they have less plugin support, but the plugin supports if you're trying to like pick up satellite communications reverse engineering and just want to get into the nitty-gritty of it. Wireshark has a really nice dissector for Iridium. They also have one for CCSDS and digital video broadcast as well. And when you're running through Wireshark, what you're trying to do is decode the specific packet structure that is being adhered to alongside any relevant contents and data that is being transmitted. And then lastly, you get to the data itself. Once you analyze the packet structure and you get to the telemetry that's being transmitted, there's different types of payload types. When we're looking at the CCSDS standard itself, it outlines 5 different data payload types, which is specified in the header. You have the file delivery system, the space data standard, telemetry, mission operations, and image data for imagery-based satellite systems. And that's it. This is a high-level conceptual overview of how you can get started for reverse engineering satellite communications. If you have any questions, feel free to raise your hand, and I'll be happy to call on you. But thank you so much. Appreciate it. For satellites, you can receive from. What? Yeah, so the question was, what are some go-to satellites, I guess, for like people who are trying to get into it? I would recommend weather satellites, so the GOES series is always fun. Also, satellites that support APT, automatic picture transmission. What are some other fun ones? Iridium. Iridium's really nice. Because with Iridium, you don't have to have a lot of expensive equipment. You just need like a traditional like patch antenna and rig it to an RTL SDR. Those are like the three main ones, I would say.
I'm sorry, I was actually wondering about particular antennas.
Oh, antennas, yeah. Yagi antennas, if you're trying to get reconnaissance on weather imagery satellites. You can use turnstile antennas, or like helical antennas if you want a more omnidirectional approach. I would say either like get like a standard Yagi that operates on like the 400 megahertz range for weather satellites. Any other questions? Yes. What about military satellites? Usually, well, if you look at the, well, it depends on the military satellite itself. You need to figure out what transceiver it's using. My military satellite experience is a little bit limited, but I would recommend, honestly, it depends on the frequency range you're trying to get, but like a standard antenna with like a good LMB. You can also use something directional, but I'm not sure. Most of my experiences with satellite signal reverse engineering is confined within like public satellites. Yes. Yes, TV satellites. I would go for getting a DVB-based dish antenna. So like, you've probably seen like some of the DirecTV like dish antennas on top of like roofs before. Something like that, specifically for DVB, digital video broadcast. And you can intercept a lot of telecommunications information alongside like video broadcasts using that approach. Any other questions? Okay, that sounds good. Thank you so much again. Appreciate it.